Hello. Good afternoon for the western part of the Atlantic, for the eastern part of the Atlantic, and good morning for the western part of the Atlantic. Welcome to the numerical modeling session that will have 5 talks, 2 from Africa, 2 from America, from Brazil, and another one from Europe. My name is Ramiro Neves, and I am also a modeler. I work in the University of Lisbon, and I will share this session. We are going to have quite a wide range of subjects on modeling. I used to say that modeling is the most important part, is the most important technology and science on ocean. In fact, I used to joke with that, but in fact, I believe a bit on that, because the good thing of modeling is that it is accessible to anybody around the world. So the equipment that we need for doing modeling can be a very simple equipment, very inexpensive, and so it's is quite a democratic way of studying the ocean. So we will have 10 minutes talks, and we will collect questions during the talks, and at the end of the session we will have a part of the session for the questions and answers. If those questions and answers go beyond our 1.5 hour slot in this meeting, we can continue here in a Zoom meeting, in a private Zoom meeting for the modelers. And so the first talk will be given by Luiz Paulo Assad from the University of Rio de Janeiro, the Federal University of Rio de Janeiro. Luiz Paulo Assad is merging physical oceanography and meteorology. In fact, he works in a meteorology department, and he also cooperates with the civil engineering department of the university, and he is a researcher of the laboratory of computational methods in engineering. And this laboratory is also hosting the local Air Center office in Rio de Janeiro. He will talk about numerical modeling to support coastal management and monitoring in Brazil. And in this talk, he is going to include also some new developments and the new initiatives that have been triggered by his collaboration with the Air Center. So, Luiz Paulo, please, you can start.
No. Ramiro, are you seeing my screen?
Yes.
In presentation mode?
Yes.
Okay. Good morning. Good morning for the western side of the Atlantic, and good afternoon for the eastern side of the Atlantic. Thank you, Ramiro, for the presentation. And I'd like to thank again the organization of the event for the invitation to participate in this session. And thank you also for the other colleagues here with me in this presentation. So the main idea of my presentation is show some applications in Brazil of numerical modeling, basically the oceanographic numerical modeling for applied for coastal environmental and maritime monitoring. And during my presentation, I'll try to give you some examples in Brazil, some demands that we have there. Some of them are common to any other place in the world, and some challenges also. So these are some topics that I'm going to talk during my presentation. And the first slide that I present is to ask some questions, in fact, to answer some questions. The first question that you must answer when we want to model something or some process, we need to know what environmental and maritime aspects we want to monitor. There are several aspects that I can say here. chemistry aspects, oceanographic aspects, meteorological aspects, geological aspects, economic aspects, health aspects, and social aspects. So the first this first question need to be responded and to us for understanding if I want to do an isolated monitoring, only see one of these aspects, each of these aspects separated, or if I want to do an integrated monitoring. The other question that you must do is, which scale are we interested in? Planetary scale, country scale, state scale, or territory and local scale? This question would have two answers. You can use a single scale monitoring, or you can use a multi-scale monitoring. Some processes that you are interested in studying nature must be treated as multi-scale processes, and so they need to be analyzed considering the property transfers, like energy, for example, between different scales, not only downscale from the planetary scale to the territorial scale, but also upscale to the territory in direction to the planetary scale. So both answers depending basically on the demand of my study. What I am interested to study in: pollution, climate change, engineering demands, environmental vulnerability. Each choice will have a specific answer. So, talking about the methods, the chosen aspect that I would tell in this presentation is oceanography and meteorology. As everybody knows, they are strongly coupled. Ocean and atmosphere are two components of the climate system that are strongly coupled, and so they need to be monitored in an integrated way. The other thing that is important is that oceanographic and atmospheric interaction process are essentially multi-scale processes. So we need to have a multi-scale approach to study them. And basically the methods that I will talk about and that is used to study is observations and modeling. When I talk about observation, I'm talking about basically remote observations with satellites and in situ observation. And when I talk about modeling, I basically talk with regional atmospheric models, regional oceanographic models, and climate or Earth system models. Basically what changes between this kind of models is the space scale. So observations and modeling must be used in an integrated way, or only in one-way direction, using observations to evaluate my model results or to validate the model results, or using in a two-way directions by interactive methods, for example, using data simulation techniques. So now that I talk about the methods that I will talk about, I would say about some challenges that we have in Brazil. The first one is the line coast that we have in Brazil. The coastline that we have in Brazil is very extensive. We have more than 7,400 kilometers of coast to study. So this is very difficult to have investment to acquire data and to model in a systematic and continuous all of this coast. The second complexity related is about the large scale dynamic process that we have influence our ocean dynamics in that region. We have this at the tropical and subtropical areas, the South Atlantic subtropical height. On the equatorial margin, we have the ITCZ, and we have also mesoscale processes, atmospheric processes, for example, the cold front systems that also will affect our ocean dynamics. And we have also all the ocean currents that act in our coast, for example, the North Brazil current and Brazil currents, and all of the space and time variabilities associated with that. After that, we have different coastal ecosystems. We have mangrove, rocky coast, sandy beaches, mangroves, tidal plains, and of course, very important urban areas along the coastline of Brazil. We need continuous financial investment, but unfortunately, we have a lack of public investment in oceanographic data acquisition in Brazil. As in science as a whole, we have a lack of public investment. During the last 10 years, a strong partnership that happened between private companies and academy give us, from the universities, the opportunity to develop some projects. In our laboratory, we have the opportunity to develop two projects, for example, using this partnership. The Project Costa Norte, that was sponsored by an oil company firm from Brazil, Enalta, and the Projeto Azul project that was sponsored by Shell and is applied in the southeast coast of Brazil. These both projects has different goals. The Costa Norte project has the goal to use numerical modeling to give support to coastal vulnerability to oil spill at that region. And the Projeto Azul has as main goal the development of an ocean observing and forecast system on southeast region of Brazil. So talking about the Projeto Azul, as any other ocean observation project, we need to develop research in all of these boxes, in these areas: atmospheric modeling, ocean modeling, observations, and of course, data assimilation. Doing that, we can support, for example, different demands of oil companies, like support drilling operations, pipeline installation projects, oil spill applications, search and rescue, and also use this kind of results to apply in different technologies, for example, ocean renewable energy technology. All of the data are always freely available for the scientific community, and we use also the concept of digital ocean. We have a site where we can disclosure all of the information of the project, and also produce some operational dashboard to support specific activities of oil industries. The other project, the Costa Norte project, is applied in the equatorial margin of Brazil. That is very complex in terms of the environmental forcing. You have the strong Amazon River discharge, the high amplitude tides, the strong North Brazil current, and the continuous trade winds acting in that region, and also all of them influencing and impacting in the ocean circulation in that region. So we need to have an approach of multi-scale environmental processes. We need to use grid nesting schemes to understand how the ocean dynamics is influenced by all of these forces. And we do that in this project. And of course, after all of the results produced, we combine this information with economic, environmental, and social aspect in order to understand the oil spill coastal vulnerability in that area. So coming back to the model, we use the NES schemes, and we have the opportunity to have a coarse grid where we apply data assimilation techniques, and then use the results produced as boundary conditions to medium grid with a 3-kilometer resolution. And in this medium grid, you have the opportunity to use observation, local observation, to evaluate our model results, and then go into the coastline to study the coastal processes, like, for example, the floods in tidal plains and mangrove areas. Of course, the work doesn't stop there. It's continued. We need to study better how atmosphere, land, and ocean act together, in a coupled way in these areas. And we need to develop high-resolution oceanographic and atmospheric coastal model. And we need also to do in the project continuous and systematic ocean, atmospheric, and hydrologic data acquisition. Talking about some initiatives in Air Center, the first one was using all of this knowledge that we have in our group to produce regional grids around, mainly in the South Atlantic Basin, in order to produce, for example, an institute that is ready to do downscaling of climate change scenarios, downscaling of hydrodynamic downscaling scenarios, and also to have an institute that permits to have operational systems in different regions around the South Atlantic Basin to support local different economic, environmental, and social demands. Another idea that we have also developed together with Instituto Superior Técnico is to study not only to produce and develop research in downscaling techniques, but also in upscaling techniques, trying to use these local, regional, high-resolution models plus the local observations that are not assimilated in global solutions in order to improve these global solutions in the whole Atlantic Ocean.
Try to be short.
Okay. This is one of the initiatives that we have. We have a joint call together with ICT that we develop, and it is now we have some students acting together, comparing different models. We also offer a course in capacity building of ocean modeling last year. We have the participation of some countries. All of these projects in the context of Air Center initiative, and it's very important to show the importance of ocean knowledge, and also to use and to normalize the knowledge of oceans around the South Atlantic Ocean. And talking about, I will shortly prepare some slides talking about observations. The main important thing to do is the South Atlantic. We have a lack of oceanographic information. It's very important for us to increase this number of observations in order to understand better our knowledge and use this information in numerical models. Of course, we have some initiatives in Brazil that are important. And we also need to use more the remote sensing data, ocean data, to improve these numerical models. These are some other examples of projects that we have in Brazil, like Project Bahia Viva. Sorry, I am a little fast. That we have that work together in an operational way with regional oceanographic models in order to do a cross analysis between not only the oceanographic and meteorological area, but also social areas, in order to understand some developments that we could do toward the sustainable development in these regions. That's it. I have much more information to talk about, but unfortunately the time doesn't permit me. But that's it. Thank you very much. We can discuss after.
Yes, that's it. Thank you, Luiz Paulo. Yes, the time is short, but we will have a period of discussion at the end, and it can be a long period. Okay. Thank you very much for your very interesting presentation, as usually. And now we move to Felix Uba from Ghana. Felix is a mechanical engineer like myself, and he got a PhD on hydrodynamic modeling. Presently, he is teaching in the University of Energy and Natural Resources in Ghana, and carries research on coastal and ocean modeling, but also some research on laser anemometry, and he is particularly interested on oil spill modeling, and he's going to deliver a talk exactly on that subject: trajectories and fate of oil spill particles in the Ghana territorial waters. Felix, try to deliver your talk in the 10 minutes.
Thank you very much. Thank you very much. My name is Dr. Felix Uba, and I'm a lecturer from the University of Energy and I'm in the Department of Mechanical and Manufacturing Engineering. I'd like to talk on numerical investigation of the state of oil spill particles. Move to the next slide. Next. We use oil every day in our lives, and not only in our cars, but in the generation of electricity and production of plastics. And as this oil goes through this supply chain, we have to protect our shared values. And some of our shared values are sensitive ecosystems. Move to the next slide. Hello. Move to the next slide. Hello. Yeah. So you have to protect our environment, and these are some of our shared values that you are supposed to protect: ecosystems, local businesses, industries. But as this oil goes through, move to the next slide. Hello. Hello. Move to the next slide. Hello. So the best scenario is that when oil moves through our environment, there should be no oil spill. Move to the next slide. Next slide. In the case when oil gets into our environment, there are some processes we are supposed to undergo to protect our shared values. Next slide. Move to the next slide. Next slide. Okay, so for us to protect our environment, we are supposed to undergo two processes: preparedness and response. And to make preparedness process, it entails 4 different processes. So for preparedness, we have to move to the next slide. Hello? Move to the next slide. So for us to make a preparedness process, it entails 4 different processes. First of all, identify the potential events where oil can get into the environment. Then 2, take scenarios. To take scenarios, it entails knowing what will happen to the oil when hello. So to make the preparedness process, it entails 4 different processes. First of all, identify potential events. So when oil goes through the environment, There are some places that can get into it. Then also the second one too is plan scenarios. How can we plan scenarios? When oil gets into the environment, what happens to it? I mean, its physical and chemical processes. So, and how can we do such scenarios? Either by the use of satellite or experiment or use of numerical models. Satellite, currently in Ghana, we are a developing country, we don't have much money to secure a satellite. So satellite is not part of it. So for experiment too, it's not also feasible in Ghana here because it requires spilling oil and later on recovery, which is also not feasible. So the best way left is to use the numerical model to know the effect of oil spill in the environment. So knowing what happens to the oil when it gets to the environment, then you can draft ways of recovering it from the environment. Next slide. Next slide. So, and this process has to be repeated several times to make all the weaknesses, to meet all the weaknesses. Move to the next slide. So for us to protect our environment from oil spill, it takes everyone, both government, industries, and then the community. Next slide. So this is a picture of the Ghanaian waters, and we can see all the oil blocks where you have different companies exploring for oil. Then we also at the boundary, we have a lot of settlement and recreational sites. And we need to protect all these sites from oil spill when it occurs. So our question is, where would the oil be beached when it gets into the environment? Next slide. Okay, so these are some of the resources we have at our coast. Next slide. So these are also some resources that you have at our coast. We have our castles and where you can also see beach makers. Move to the next slide. Next slide. Okay, so currently in Ghana, we don't have any in-house model, any in-house numerical model to help in the prediction of what happens to oil in the environment. So it is good for us to have a model that will help us to know what happens to the oil particle when it gets to the environment. So this will help us to draft a sensitivity map, will help us to know which places are vulnerable to oil spill. And the model to also help us to know where to place resources whenever there's a spill and recover them from the model. In any learning process, we have to always make or draw our system. And so in this case, this is our system, the Ghana coastal waters. And also move to the next slide. Okay, so after creating our system, we also have to extract our data. And when it's because of the size of the domain, it is extracted from the internet. And what about satellite data? They are not all that refined, so you have to evaluate this bathymetric data with local data. So in this case, I use some of the data from the harbors to evaluate this data to make it more refined. Move to the next slide. Move to the next slide. Okay, one thing that is plagued with one particular thing that is plagued with computational simulation is memory allocation and also computational time. So because of that, in my work, I try to use the nesting domain to reduce these two effects. And also, after identifying your system and the identifying system, you have to also look for your boundary conditions. Next slide. Next slide. Because my PowerPoint is not controlled from my end, so I'm having problems identifying it. Okay, move to the next slide. Next slide. Okay, so as I said earlier on, so the work was done in the nesting domain. The first, the two-dimensional, and then the second and the third is a three-dimensional. So after running the first domain, which is barotropic, this is what you get, and it's only the water level. Move to the next. So the second and third, which is three-dimensional and bioclinic, which involves all the properties of the sea. So this picture is a particular solution that is extracted from the hydrodynamic model. And this very solution has to be validated before we can use it to couple to a oil model. Move to the next slide. Okay, so to validate this solution from the hydrodynamic model, I use 4 different points, A, B, C, and D to validate it. So what am I going to validate? Water level, salinity, and then temperature. Move to the next slide. So this for water level, and then the model is the red, the blue is for the field. The model is higher than the field, and there's a reason for it, because currently there are a lot of expansion works at the harbor where these devices are installed, and whenever expansion work is going on, it affects the distance between the instrument and the floor. And also, if you have docking ships, there are reports that the cause also affect the reading. So this is why there's a disparity. So the difference that's between them is 14%. So we have the salinity. Move on. We have the temperature. Move on. So we have hydrodynamics.
Please try to be synthetic.
Okay. So we have they have the current. They have the current. Also, move to the next slide. So this is the current and the direction. Move on. So at this point, we have the hydrodynamic model, and it has been validated, and it really predicts what is happening in Ghana here. So now we can couple this hydrodynamic model to the oil model to predict what happens to oil when it gets into the environment. Next slide. So before we start, we have to look at possible places where oil can get into the environment. So I chose A to H. These are the possible places that I use, and the locations are seen there. So let's look at what happens. Next slide. So at point A, where the discharge point is, with time, the oil's area increases, it moves, and after some time, it gets beached at the shore. Move on. Next slide. Then you can see the other discharge point. After some time, it gets beached. Move to the next slide. Then you can also see the discharge point A. After some time, it gets beached at the shore. Move on. So we can also see the other one. But in this case, looking at the location, the discharge point, though the oil moves, it moves out of the EEZ of the Ghanaian waters, the next country. Move on. So now let's look at the fate of the oil in the environment. So with time, the thickness falls with time. Next slide. And also the area also increases. Next slide. Then we have the volume. The volume changes. The volume of the oil falls with time because of evaporation. The volume of evaporation also increases and stops at a point. The reason why evaporation stops at a point is because with time the oil gets emulsified and become very heavy and it's not volatile. Then the oil that is beached also increases because of emulsification. Next slide. So which I can conclude that we're able to implement the hydrodynamic model in 3 domains. Second and third were forced with atmospheric and oceanic parameters, and also it was coupled to an oil model to look at what happens to oil spill when it gets into the environment. Move to the next slide. So looking at looking at all the possible points that I use for my work, I can see that all the coastal line or the shoreline in Ghana is vulnerable to oil spill particles in the case where oil get into the environment. Next slide. Okay, so this is a summary of the results. Next slide. Okay, so it's only at this point where when oil gets into the environment, it go out of the EEZ of Ghana waters. Thank you. Next slide.
Okay, thank you very much, Felix. I think we have many things to discuss about this, your modeling activity. And now we move to another presentation in quite a different subject by Mary Gasalla. Mary Gasalla, she is a professor at the University of São Paulo in Brazil, and she heads the Department of Fisheries and the Laboratory of Fisheries and Ecosystems. She is interested on the theoretical and empirical approaches to marine resources governance, and also to the integration of natural and Social Sciences. She is currently a member of the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services, and she is going to deliver a talk on scenarios-based models for marine biodiversity and ecosystem services. In her talk, she will address the importance of drawing scenarios to assess the future of marine biodiversity and ecosystems, including scenarios for climate change. So, Maria, the floor is yours.
Yes, good afternoon, and thanks to the Air Center and All Atlantic Summit for the invitation. So today my talk is not on computational science, neither data science perspectives, but rather I'm going to talk on the role of scenarios and scenarios-based models for marine biodiversity and ecosystem services. And from my perspective, as being formerly a fisheries biologist, scenarios and models have been present in my scientific understanding on how to look at different fishing pressures and policy impacts on the fisheries stocks and yields. And some of them are based on scenarios. And scenarios planning is a way to structure the uncertainty on directions that future developments will take. And with the recent pandemic, scenarios development has been central in the media and all governments, private sector, academia, and in these sort of scenarios that are really important to have the different plans and exit plans and scenarios. You can have the epidemiologists playing a key role, a central role there, right? But also climatologists have been key to scenarios development on the different climate futures. For instance, the Intergovernmental Panel on Climate Change, the IPCC, used 4 pathways for climate modeling, depending on the volume of greenhouse emissions. They called it representative concentration pathways, adopted by the IPCC. And then it evolved to the shared socioeconomic pathways that can show 4 different pathways that the world could take with global warming. And in this way, the integrated assessment models can be run using the different SSPs scenarios, right? And also IPCC offer 5 different ways of looking at scenarios. For instance, these sort of 3 different scenarios, 1 more worst case scenarios and 1 mid case scenarios and best case scenarios. For instance, 1 of late and coordinated action, 1 of more delayed and decisive action, and more on early effective action. And for each of them, they can have examples, different projections, for instance, for storms and for ice sheet melt, flooding, etc. And also looking at this early effective action, they can also predict that in this scenario, the risks are reduced for a proactive adaptation, but we still have heat waves affecting the tropics. And there are different ways of looking at Arctic melt and coral recovery, for instance. And also more plausible and likely trajectories make better baselines for a huge policy push needed to keep global temperature rise below. So these researchers show the likely possibilities and pathways to reach these possible futures. Also, we can link the models with the risks that the biodiversity can have of the different ecosystems can have. Here you can see, for instance, while the increase of temperature have different risks and impacts in warm water corals, seagrass meadows, salt marshes, and mangrove forests, being the warm water corals sensitive in an early sign of climate change. And also in terms of biomass, animal biomass, because different models can lead to divergent conclusions about marine futures. This project here calls a MISHFIP project, using an ensemble of multiple climate and ecosystem models, revealed that we're going to have a trophic amplification of climate change, and also that global marine animal biomass declines under all emission scenarios. Yeah. And it links also from the phytoplankton to the large consumers, and it really these ecosystem models predict that at higher food web levels, it will amplify the effect. Also, climate change can affect the distribution and abundance of marine life, with consequences for goods and services provided to people. And here you can have the projected changes in maximum catch potential of marine fisheries. And this model for all the basins, all major basins, and the model predicts that here, you have the latitudes here, and the model predicts that for the tropics, they can have a strong decrease in the catch potential for fisheries, which is really crucial for our communities in the tropics. Also, recent models also shows that by looking, this is a study looking at reef fish, and they also use different types of IPCC scenarios, looking at the thermal range for different types of fishes. And they found that the trophic interactions will expand geographically, but be less intense as ocean warms. And it can have differently depending on the trophic yield of the fish. But also in the models, you can include economic data on the ocean. For instance, this is a model looking at demand scenario. And this uses seafood demand scenarios. So depending on the demand, the supply model can show differences in the composition of the seafood. Here is for instance, this baseline, and here is the current situation, and this is a future demand, and this is extreme demand. And in the scenario of extreme demand, you can have more contribution, for instance, for bivalve mariculture and the two types of mariculture, and a reduction of the contribution from fisheries. And these scenarios also can be used for measuring biodiversity targets. And they can assure that these biodiversity targets can be well fundamented and implemented. This was a product also by IPBES, which is the world's first and only intergovernmental science policy platform for biodiversity. So the indicators, you can look at the indicators from the past to the present, and then have these different trajectories looking at the future scenarios for these targets. And the IPBES has a task force on scenarios and models, especially looking at new types of scenarios. And why do we need new scenarios is because we really need to develop scenarios that look at desirable futures, so positive futures as well, in order to have, you know, the different, that we can represent the different policy and management responses and how we can get there. And it emerges for the studies also from IPBES on the different perspectives on human relationship with nature. And this is the main idea, that the nature can have different types of values, as being like intrinsic values and also instrumental values from humans and relational values for humans. So it's what we call nature for nature, nature for society, and nature as culture. And based on that, the IPBES Task Force on Scenarios and Model is developing this nature futures framework, where in each corner of this triangle, you can have these contrasting values of nature. So you can have nature for nature here, nature as culture here, and nature for society here. And then we can try to build on or visioning these nature futures for different sectors, such as ours in the marine one, but also culture, food production, and prosperity work, and other sectors. And this have been very interesting experience to me, look at and creating scenarios in the different corners and sides of this triangle. Also, this task force uses this kind of cycle for scenarios developing, going from visioning and description desirables futures, elaborate these visions, refine this framework, and also have these future iterations from the development of the scenarios and models. But how about the Atlantic Ocean? So in terms of the Atlantic Ocean, I can mention that a recent project funded by the European Commission under the Age 2020 call has just started. And Mission Atlantic is a project towards the sustainable development of the Atlantic Ocean, mapping and assessing the present and future of Atlantic marine ecosystems under the influence of climate change and exploration. And in this project, we'll work with different scenarios and also linking hydrodynamics and biogeochemistry simulations and models and forecasts, also to the large predators. So it's a way to link these models to fish biomass as well. So it is predicted that we have, we're going to analyze and have simulations. For instance, this is just an example of the type of simulations looking at key migratory fish species and how these models can provide biomass estimate, for instance, for these tuna species. And here in this project, we'll also produce future scenarios based on contrasting shared socioeconomic pathways, and we're going to look at potential future of this ecosystem states in all the Atlantic basin, specifically in some case studies across the Atlantic. And
Mary, shall I ask you to be synthetic?
Yes, it's my last slide, really. And just to make sure that these scenarios development at the Atlantic Basin will be an important process for this experience and this opportunity for international collaboration. And I think that it should really contribute to address Atlantic opportunities. So thanks for your attention, and I can take your questions after the session, right? Thanks very much for the opportunity, and thank you, Ramiro.
Okay, thank you very much for your talk. I'm sure you are going to get a lot of questions. And now we move to the other side of the Atlantic again, to South Africa, and we are going to learn about operational modeling in South Africa by Jennifer Jackson-Veitch. She is a numerical modeler at the South African Environmental Observation Network, where she leads an interinstitutional initiative to implement an operational ocean forecasting system for South Africa in cooperation with other departments from South Africa. And she is going to give us to explain how this will be done, and we will also visit a bit how data is being managed in South Africa.
Thank you, Ramiro. I trust that you can all see my slide.
Yes, we can, and we can hear you clearly.
Okay, is it in presentation mode? It doesn't look like it from my side.
No, not yet.
Ah, okay, there. So not being sure of what angle to take for this 10-minute slot, I've decided to use the project that I'm the lead on as a way of sharing some perspective on South Africa's numerical modeling community, its development strategies, as well as some challenges. So the SAMISANA project is a joint Department of Environmental Affairs and Fisheries and Forestry, as well as SAEON. And it really represents the beginning of our adventure in operational ocean forecast system for the Shelf region in South Africa. But before I talk about SAMISANA, I would like to share a little bit about the context and how we got here. So in 2014, Operations Pakisa was ratified, and the oceans economy was seen as the solution to all our problems. So it was seen as the potential to contribute billions to our GDP and also to create over 1 million jobs. However, unfortunately, this came with very dirty offshore industry. So the Department of Environmental Affairs, offshore ecosystem, are obliged to ensure that this exploitation happens in a sustainable way. And therefore they sit squarely in this Marine Protection Services and Ocean Governance task team of the oceans economy. So as part of this, they contracted the CSIR to develop the National Oceans and Coastal Information Management System, otherwise known as OCIMS, which is essentially a portal for stakeholders to, it's a portal of decision support tools for stakeholders to make more effective decisions for the marine environment. So as an example, the tools are very much based on the end user. So this is an example of the harmful algal bloom tool, which is geared towards assisting the South Coast aquaculture industry. And it uses satellite information to provide a risk assessment of the likelihood of harmful algal blooms occurring in key locations. So we have a front end, and that is OCIMS. So OCIMS informs coastal management, search and rescue, compliance and enforcement, and disaster management. So this is great. But we also have a back end, the Marine Information Management System. It is a publicly accessible repository which stores all of this ocean and coastal information that goes into OCIMS. But the thing is, we're missing something. We're missing the operational ocean forecast current models that can be used to feed into the OCIMS decision support tools. So this is where SAMISANA comes in. So SAMISANA stands for Sustainable Ocean Modeling Initiative, a Southern African approach, and its major goal, its a vision, its long-term goal is to develop an assimilative operational ocean forecast system at a high resolution for the entire South African exclusive economic zone. Now, for South Africa, this is a very big task because we have very little capacity in numerical modeling, and the capacity that we do develop locally, we find it hard to retain these modelers. So this comes to our vision and the very important word of sustainability. So to achieve this, our immediate vision is firstly to produce some operational products as a demonstration that will feed into OCIMS, but also, and equally important, to build local capacity. So I have it on good authority by a colleague that SAMISANA means something like to work together in Sepedi, which happens to be one of our 11 official national languages. And this is exactly the approach that we need to take, not just in terms of the model development, but also in terms of capacity building by training students in various projects that are collaborative efforts with international and local colleagues. So the operational ocean product development that we are doing revolves around hindcasts that we use to monitor the state of the ocean, but also nowcasts and forecasts that will be integrated into OSIMs as decision support tools. So our strategy is to, firstly, this is
Jennifer,
sort of like, yes, hi.
Are you aware that your slides are not passing?
Oh no, I'm not aware at all. Has it not passed? No, I wasn't aware of that. Thank you for giving me the heads up.
Okay, now you are in presentation mode.
Are you seeing this slide with the Eurogoose logo?
Yes.
Oh, apologies for that. It would have been much nicer if you had seen the correct slides. So our strategy for developing information that adds to... No, I know, thank you. Is to add value to existing operational satellite and model products. This is the low-hanging fruit, but also to downscale forecast models optimized for South Africa's EEZ and coastal regions. Okay, so you should be seeing the next slide.
Yes.
Matt Carr and Christina Rasso are producing products based on satellite and globally available reanalysis products. And these products are being operationally disseminated on a test web server, which will eventually be fed into OSIMs, but also will make marine science more tangible to stakeholders and to the general public alike. So like I said before, our biggest goal is to develop a fully assimilative operational ocean forecast system for our EEZ, but of course the lead time on this is very long because of the many steps involved along the way, but also because of some of the challenges that we face here in South Africa, which include infrastructure requirements, in situ data or lack thereof, and also capacity. So we really see the need to develop a demonstration forecast system, something useful that we can demonstrate, and hopefully that will spark some interest in high-level organizations and therefore to leverage some funding. It's also important that we choose a demonstration site that is contentious and that will actually spark more visibility. It wasn't difficult for us to choose Algoa Bay as the site. So here it is on our south coast. I hope you can see my mouse. Here's Algoa Bay. It is the region, or it's the home to a number of bird colonies on a number of islands. This yellow line demarcates one of the biggest MPAs around our coastline. And these little orange icons represent the location of an oil bunkering or ship-to-ship refueling industry, which of course has major ecological risks. And in fact, in July last year, there was an oil spill that impacted the bird community massively. And in fact, the role players here who were involved with the cleanup and mitigation were desperately looking for an appropriate operational ocean forecast model, but they couldn't find one. Okay. Another reason that Algoa Bay is an optimal site is because it is data rich. It is one of SAEON's shallow marine and coastal research infrastructure sites, which means that it's full of data and that we could evaluate our models with confidence. So Giles Fearon at SAEON is leading this, the development of this limited area forecast model. The approach is to use Croco and a curvilinear grid, which increases in resolution from the boundaries towards Algoa Bay. He's being very rigorous in his approach. He has run a limited period hindcast simulation based on 3 different globally available reanalysis model products. So the 3 products are the US Navy's HICOM, Mercator's GLORIS, and BlueLinks Bran. He's run the simulation for each of those boundary conditions, and he has done a rigorous evaluation with various data sets, but I'm just showing you the one. And what we're looking at here are in black in this time series is the observation, the UT observation at the mouth of Algoa Bay at a depth of 10 meters and 10 meters. The correlations are really good. You know, on the bottom right here, we see the correlation from the surface to a depth of 70 meters. The correlations are good. They're best for GLORIS, the simulation forced with the GLORIS boundary conditions. And in fact, they improve even more if we compare against an ensemble mean. So based on this work, Giles Ferron is going to move forward and operationalize this model using the GLORIS forecast product at the boundaries. And to take this further, to add to the value chain of this model and to show stakeholders that there really is usefulness in knowing what the state of the ocean currents are going to be in the next 3 to 5 days, is we're going to couple it with an oil spill model so that users can get a sense of what the trajectory of a hypothetical oil spill will be in the bay. So something like this. Okay, so here we've got an oil spill happening and we can see the trajectory. So the idea is to have this value add on our model, which will feed as well into OSIMs. So once the system is operational, the methodology can be employed in other locations, which would include the South Coast aquaculture industry, as well as St. Helena Bay, where harmful algal blooms are a big threat. So we could use a similar methodology for harmful algal blooms. So
can you listen, please?
Sure. I'm nearly finished.
Okay.
So I'm going to step just briefly away from our operational initiatives and the South Coast and just bring the focus back to the Atlantic side. So in South Africa, a lot of our Atlantic research and modeling goes into the Benguela upwelling system, of course. But we need to remember that in South Africa, we are lucky in that we have an eastern and a western boundary system. And it's the only place in the world where these 2 systems interact directly. So even if we're studying the Benguela upwelling system in the Atlantic, we cannot ignore the Agulhas current system because it has a really big role to play in the southern part of the Benguela system in terms of adding major turbulence. But let us also not forget the role of the Agulhas leakage in the large-scale Atlantic overturning circulation. And the point I'm really trying to make here is that although this is an Atlantic-focused symposium and grouping, we really cannot neglect our boundaries. And even if I'm biased, I would say the southeastern boundary of the Atlantic is particularly crucial. So I'd like to just end on this slide, and it's a beautiful image produced by NASA's Ocean Color Web to remind us how, like fractals, the ocean produces swirls within swirls within swirls within swirls. It's really complicated. And in order to do it justice, we really have to produce or design an integrated system that integrates observations, in situ observations, Earth observations, and models in a clever way. Thanks very much. Apologies for the problems with the slides.
Okay, it was fine. Thank you very much. And now I'm sure you will have a lot of questions too. And now we move to the last but not least presentation by Nadia Pinardi. I think everybody knows Nadia Pinardi. She is a professor of oceanography at Bologna University, and she is a major driver of numerical modeling in Italy and in Europe. And she has been part of all modeling initiatives that I know in the Med-Sea, and of many of the larger projects funded by Europe, for the whole Europe. So operational oceanography has no secrets for her, and so we are going to learn a lot from her in this talk. Nadia, please.
Yeah, sorry for being late. Okay, thank you, Ramiro, for the introduction. Thank you, the Air Center, for this really important initiative that brings us together once in a while and exchange ideas to build a better society in general. So I will be today trying to make a short story of a long one, which is going from weather to ocean prediction toward the coastal resilient society that we all aim at. Let's see, yes. So I will try to skim over the science of ocean predictions, the silent revolution that will test the theory for us every day in our operational centers. I will try to also skim over the societal drivers that require an improvement of disaster risk reduction strategies based on a science, on a sound science support. And then what are ocean predictions today? And some of the latest solutions, I think, are finally showing the value of operational oceanography. And then final consideration and one brief message about the UN Ocean Decade program that we are organizing. So the science of ocean predictions is a new science paradigm that started at the beginning of the last century. And clearly it was Bjerknes that talked about hydrology and meteorology. And the principles are still the basis. You have seen them in the previous presentations. Is we need observations to construct the best initial conditions. We need to have a predictive model with skills, and we need to continuously validate our model, which means the forecast, and test the hypothesis. So ocean and atmosphere predictions are the only way really to test the theory and improve the basic understanding of the ocean and atmosphere systems, which can bring us toward better disaster risk reduction, science-based system overall. This is a very interesting Nature paper in 2015, which overviews the quiet revolution at this point of numerical weather prediction, but soon to become ocean prediction too. So the priorities, you all know that floods, including coastal, are one of the major impacting disasters on properties, but also lives. And so the Sendai framework for disaster risk reduction sets priorities, which has increased understanding of the different risks. And we have seen also from your talks, from the other talks, different ways to solve and understand the different risks, increase the science-based early warning systems that can alert us on and prevent major disasters, and increase the access to multi-hazard. So the accessibility is also to these systems is also an issue, a key issue. For 40 years, meteorology has constantly improved, arriving now to valuable products for disaster risk reduction. And we all know these beautiful curves that from 1981 to 2015 show the constant increase in skill in different lengths of forecast, 3 days, 5 days, and 7 days. The two curves are for Southern Hemisphere and Northern Hemisphere. And you see now that the two hemispheres have approximately the same skills. And this is due mainly to the satellite data that were appropriately assimilated recently, I mean, starting from the 2000. Okay, so how do we advance in ocean coastal disaster risk reduction? We have to follow a little bit what meteorology has done with the specificity of ocean, naturally. So we have devised an ocean value chain that makes clear sort of blocks, is more of a systematic approach to get societal benefit products. So we have the input data systems and the data management, which is essential, the data collection, observations. We need, however, to have these generic information services that will assemble the data and make them available at appropriate time for the numerical models to assimilate and validate. And then we need the customized processes that are downstream. We cannot do customized products without having such a chain well organized. And first of all, it should be organized at national level, but with international standards, because nobody has all the key points in making up this. At the international level, we can probably set it up, and this is what we did in Europe. So with the Copernicus system, I'm showing you now what are ocean predictions. We have already heard about GLORIS. GLORIS is part of Copernicus Marine Environment Service that provides everyday forecast analysis and reanalysis. And this is another system that we run at CMCC, where we reach 1/16 degree model with satellite. We assimilate all satellite real-time and in situ data daily. An equivalent one is the one that is used. But we have even more advanced systems in the Mediterranean, where we started among the first. We have already fully coupled hydrodynamics, surface waves, pelagic biogeochemistry, and we do have forecast, 10 days forecast for each of these components. Okay. So where are we today? With after I will show you a shorter time scale now, from 2013 to 2019, which is the Copernicus CMCC system. Now we see here that the skill has been, this is root mean square error for salinity, and this is for the third day forecast of salinity. You see it constantly improving. And there are two shadowing areas here. One is the blue, and one is the shadow in the salinity analysis skill. And we see here that data have increased, which is part of the gain in skill or the reduction of the root mean square error. And but also models have increased their quality substantially. Okay, so to show you that the models are really crucial and they have to be adapted and calibrated, validated. This is instead a longer time series. Our first forecast system started in 1998, really. And here you see a sequence up to 2010, when we had a certain kind of operational system in Italy. So this is sea level, and it is the root mean square error, and this is centimeters. Okay, so here you see different curves. I'd like to point out to the red curve and the green curve. So these two curves have same variational data assimilation, and approximately they assimilate the same amount of data, but they have two different models, one much better than the other, NEMO versus OPA 8.2. And without talking about the first model that we took, which was MOM. So the message is that 30% error decrease in 10 years approximately was due to model improvement, and is still a major cause for error reduction. Okay, so where are we now? Now we are here. We are now at the level of crossing the land boundaries and getting the water that arrives at the ocean, and it is near the urban settlements. So we are at urban oceanography scale. And this is all allowed, as I will show you in a few seconds, because we have capabilities to nest in global ocean operational circulation models. It would never have been possible before, but also because we now use advanced models for the coast, which are unstructured grids, nested in structured grid global regional models. So this is an example of a hurricane arriving along the coast of, this is work we do with our colleagues at Georgia Tech. This is Georgian coast, Savannah area. You see the switch domain, you see the complexity of this structured grid model. You see where a tide gauge at Fort Pulaski is located. And here you see the hurricane arriving on the coast and hitting. And for the first time, and for many hurricanes around this area, we can have such skill, meaning that this hurricane that everybody was thinking it would destroy the coast did actually do nothing. And in this paper that we are now analyzing, we can also get for example, for Matthew, another hurricane that was in 2015, we can instead forecast the high level with quite a good accuracy, which is about 10 to 20% error in the maximum sea level height. So, and you see how small is this domain, because outside there is a global model giving the right boundary conditions. So we have hope that in the next few years, we will be able to really arrive at early warning systems that have capacity to be used as for disaster risk reduction. So in final considerations, operational oceanographic services offer nowadays products of unprecedented accuracy and extension from analysis to reanalysis and forecast. Model improvement is still a critical issue for both forecast and analysis, and we should continue. But we have something really new and promising. Limited area and structured grid modeling promises to be the final solution for coastal area disaster risk reduction, early warning systems, because we have now large-scale forecasting model for nesting. We can adequately nest to the larger scale flow field. And let me conclude by saying, I hope you will join us in this big adventure. We are launching the UN Ocean Decade program that is called Predicting the Global Coastal Ocean. I think it's the moment now. It will be a great decade. And I hope the Atlantic would be one of the area of major effort for this. Thank you very much.
Okay, thank you very much, Nadia, and to the other speakers. And it was a very nice set of presentations.